All right, let's get started. We are recording, and okay. Okay, today we'll be talking about something a little bit different. So, everything, all the analyses that we've talked about to this point kind of falls under a broader category of sort of models and problems, which we call supervised learning. And today we're going to learn about this other category of models called unsupervised learning. So unsupervised learning. So the main distinction between everything that we've done versus this class of approaches is that in supervised learning, you are looking at relationships between your explanatory variables and your response variables, right? And so that covers the broad gamut of regression approaches that we've talked about thus far. With unsupervised learning, we have no response variable. Okay, so there's no y in this set of models, and so you can't do things that that you would ordinarily be able to do in supervised learning, like validation, right? There's nothing to compare against because you don't have any y, any sort of even testing or training set, right? And so what is the point of unsupervised learning? So this is to examine undetected patterns in data. And this focuses, as I was just mentioning, on settings with only explanatory variables. So no response variables.
What do you mean by setting?
Setting, like this, your data basically, focuses on data. So here, not interested in prediction. What we're trying to do is identify subgroups among variables and unable to conduct validation. Okay, so the main set of techniques that we're going to be talking about today is clustering. So clustering is not the only type of unsupervised learning, but it's probably the most common. And there are a whole bunch of different approaches to thinking about clustering. And we're going to cover kind of a broad set of them today. And they should be able to serve slightly different purposes depending on the type of data that you have. Okay, and so we'll dive right into it, unless anyone has any questions at this point. No. Okay. So clustering approaches. Okay, so the first one, and I would venture to guess some of you guys have heard of this before, K-means clustering. Also known as centroid clustering. So who's actually used K-means before? A couple people? Okay, great. So this is, yeah, probably one of the most common clustering approaches. So this is simple approach to partition data set into K distinct non-overlapping clusters. So it's not like probabilistic or anything. This will assign every data point to one particular group, okay? So the only parameter that you have to pre-specify is K, which is how many groups that you want. So K must be pre-specified. Okay, so just for context, here's the math. But like many of the other ones that we've talked about, or other modeling techniques, the procedure itself is probably a little bit more straightforward than what is being described in the math, and so we'll get to that in just a second. Okay, and CK is the number of observations in the kth cluster. Okay, so basically what's going on here, we'll do like a pseudo algorithm to describe the process. So one, randomly assign 1 minus k to each observation. Okay, and then 2, we iterate until no more changes. Okay, so for each K cluster, compute the centroid. And then B, assign each observation to a cluster with closest centroid. And so this is by Euclidean distance. And so here in particular, note the scaling. Normalization is critical. Because we're doing everything based on distances, if certain variables are in very different units than other variables, then you'll want to think about normalizing the data so that your clusters will be appropriately grouped. Okay? Okay, so let's just do an example of this, and then I think that the algorithm will become a lot clearer. so let's say I have two variables, x1 and x2. I'm going to be careful not to use y because that implies, right, a response variable. And in this case, we don't have a response variable. And let's say in this data set, you were just to plot all of the data along these two axes. And let's say, hypothetically, it looks something like this. Okay. So you've got this data set. And what I want to do is I'm going to enter into my algorithm. I'm going to randomly assign each observation into my groups. So let's say k equals 2. And I'm going to divide all of my data into blue dots and red dots. Okay, so I'm just gonna like randomly pick some points. Okay. And randomly assign these points. Let's do something like this. I'm going to do a couple more red ones over here. All right. So now that I've done step 1, I'm going to enter into step 2, iterate until there's no more changes. So for each K cluster, compute the centroid. So basically, what I want to do is add up all the x1s, and then let's say for blue, and then divide it by, how many do I have? There's 7 plus 6. So, oh no, that one's not my actual. So 7 plus 5, so 12. So I'm gonna add up all my x1s, divide by 12, and then for red, similar, right? 7 up there, 4 over here, so 11. Okay, and then so if I do that, so I'm gonna assume that because there's like slightly more blue points in this cluster here than up here, that the average or the centroid for all of these blue points is gonna be, let's say, something like over here. Okay? Anyone disagree with that? You can move it if you want. And then the red ones, there's more red guys in the top right than there are in the bottom left. And so let's just say, hypothetically, if I actually calculated it, that the centroid is over here. Okay? So then what I do is I go to step 2b, assign each observation to a cluster with the closest centroid. Okay, and so I'm going to go point by point. So hopefully you guys can see all of the points on the bottom left are closer to the blue X, right, are closer to that centroid, and all the points on the top right are closer to the red centroid, yeah.
Is red and blue data that they had, or something that we assigned to them?
We assigned it randomly. That's step 1.
Is that supposed to be 1 through K and not 1 minus K?
Yes. Okay. So if we do that, I reassign all of my points. Okay, great. Okay, and so we need to iterate, right? And so I'm going to go back to step 2a. I'm going to calculate for each cluster, I'm going to recompute the centroid. The centroid of the red points is now moved. Let's say it's somewhere around here. And the centroid of the blue ones is maybe somewhere around here. I'm going to reassign each observation to a cluster with the closest centroid. So now all of the blue points, right, are going to get assigned to that blue one. So nothing really changes. Okay, and then I can go back to step 2, and I'll see that if I iterate one more time, the location of the centroid and the assignment of the points do not change. And in that case, we say, okay, we're done. Okay? So hopefully you guys can see this is a pretty simple algorithm, but a powerful tool that can pretty quickly and efficiently group your points into these clusters. Any questions? All right. So let's take a look at implementing this. K-means example. And I have put in a couple of data sets into Canvas. So there's 4 examples. There's 2D-4C, 2D-20C, banana, and Cluto T7. Yeah, these are all kind of interesting data sets. That we can use here. And if you want to see kind of what these guys look like, we'll set that up really quick. X equals EX1 $X, Y equals EX1 $Y. Okay, so let me just copy and paste this a few times. Okay, so we're going to apply this clustering algorithm to 4 different examples, and we're going to see how well, and by well, this isn't necessarily something you'll always be able to do in terms of like, I'm kind of saying well in like a validation terms, right? But really, this is you can't really do validation because it's not like any points in any of these plots belong to any particular group. But the point of this is that visually you'll be able to see kind of the trade-offs between different clustering algorithms. Yeah?
What are some like practical applications of this clustering?
Yeah, so a lot of data that are like spatially oriented that you want to sort of distinguish in some way, you might you might be able to apply kind of like a clustering algorithm. So like electric vehicle chargers, for example, you might be able to cluster them spatially in certain ways and then use that to then describe characteristics of the clusters, right? So yeah, there's lots of different reasons why you would do clustering. And I would say a lot of this is going to be focused on more exploratory aspects because you're not doing like some kind of validated procedure. Yeah. Any other questions? Okay. Let's do our k-means. So here all I'm doing is I'm feeding in, there's two inputs into the k-means function. One is the data that I want to do my clustering on, and then the number of clusters. So I'm doing it for example 1, and I'm going to do 2 clusters. Oh, what did I do? Oh. And if I just spit out the object, the information that here's the information that comes out of running the k-means. So 1, you've got your cluster means, and so these are the centroids of each cluster. 37.24 on X, 12.5 on Y, and then the other cluster has an 85 on X and 52.7 on Y. And then the clustering vector tells you which group every individual data point in your data set is assigned to. So data from rows 1 through 650, 2, 3, 4, 5, 6, 7. 1 through 657 get assigned group 1, and then the rest of them get assigned group 2. And then there are some extra statistics that we'll talk about in a second. Let's see. Okay, and so if I plot this, looks something like this. Okay? So with 2 clusters, my centroid for red is probably somewhere around here, and my centroid for green is probably somewhere around here. And so all of the points closest to those are going to be assigned to the group. Well, that's closest to those centroids, right? As we did in our example. So that's what this looks like. All right.
How do you go about plotting these centroids?
So if you wanted to plot the centroids, and I can find my mouse, there it is. You could grab it from the cluster means here, So, all right, the actual centroid would be 3712, and then 85 would be right around here, and 52 would be like over here. Yeah. But people don't usually plot the centroids, but you could if you wanted to.
Because we usually only have two variables.
No, you could cluster on as many variables as you want.
So that's what I'm saying. Is with only two variables, it's easy to plot. Any more, than it gets
Yeah,
obscured.
that's right. That's right. Okay. Yes.
Since there are no like really any validation methods, is there a way to like kind of figure out like what the ideal amount of groups is? Because we just said like 2, and here here it's easy to see that like 4 maybe would make sense, but for some data sets you probably can't see like how many groups make sense.
Yes. Why, I'm so glad you asked. Okay, so yeah, no. So there's no cross-validation answers here today, unfortunately. So I'm gonna one second here. So I'm going to show you guys a custom function that I've built that's basically going to test a bunch of different clusters. And the thing that I'm interested in grabbing from this is the within sum of squares. So that's this metric. And so there are these set of statistics that come out. So the total sum of squares, the within sum of squares, the total within sum of squares, that tell you something about the characteristics of the clusters. And I'm specifically grabbing the within SS, and I'm gonna try and test k-means where I have anywhere between 2 up to 10 number of clusters. Okay. And I'm going to plot the number of clusters against within sum of squares. Oh, hang on. Okay. So the within sum of squares is telling you about, it's a metric that measures the sort of average distance from your, from the centroid of your cluster for all of the points in that cluster. So I will say, oftentimes the choice of your K is determined by some kind of, so oftentimes you want to have a certain number of clusters, and you may have some intuition about the right number of clusters. But when you don't really have that intuition, or there isn't really any sort of, there isn't any like precedent for the number of clusters, one thing that people do is called the elbow rule, which is still pretty subjective, but it's at least, it's subjective in the sense that there isn't anything like real quantitative justification for it, but it at least gives you something that you can justify for using like a standard like operating procedure defined. Okay. And so the elbow method is, okay, test a bunch of clusters and then plot out the within sum of squares as a function of your number of clusters. So you end up looking like this. And so this one is like very, like particularly salient. They don't always look like this. But the idea is that if it kind of looks, it always looks like this, and you're supposed to find if you imagine that it looks like an arm, it's supposed to be the kink where your elbow is. So in that case, that would be 4 here. Yeah, and so that's one common way that people use to decide the number of clusters when you really have no other information to go on. Yeah, and so let's see here. If I were to plot so this is what happens as I cluster different numbers of groups to the data. So this is if I have 2 groups, and this is the same thing as we saw before, the colors are different. This is if I have 3 groups, you can see that these 2 remain the same, but now this and this group are different. And then 4, which is kind of our ideal one, you can actually see that it does a good job at distinguishing all of the 4 sort of groups. If I have 5 clusters, it's a little bit hard to see, but what ends up happening is I have distinct groups here, but for this group, it gets split in 2. Okay? And then if I have 6, it splits this one in half, and it also splits this one in half. You can see there's 2 shades of green here. 7, it will actually now return to keeping this whole, and then split this one into 4 groups, and so on. And so you start to get some weird groupings. And right, this is all artificial, but it's following the rules of the k-means algorithm as we've described. Okay. Any questions? Yeah.
Yeah. Question about the cluster 3. It looks like not quite makes sense. We see the right corner, the 2 groups, they are quite close with each other compared with the left 2 group of data. Why in the cluster 3, the right top corner, the 2 group data, they split to 2 different groups?
Yeah. I'll just note that so this isn't necessarily directly answering your question, but sometimes these things can be a little bit trickier to distinguish because these axes are not of the same scale. But I don't think that's necessarily, it can also have something to do with the number of points in the group as well. So it's kind of hard to tell anything about density here. I don't know exactly why, but I can tell you that it is right, and that if you actually went and like manually did it, I should do that sometime. I should. Yeah, we could actually animate the procedure of iterating through the step 2 in the algorithm, and I think that you will see that it will sort of arrive at this. yeah, it does look a little weird that it's doing that. But that's what the algorithm is doing, yeah.
Could you remind me again how the clusters are grouped together? Like when they have more cluster groups, as the k-value goes up, like how do they determine?
Right, so it may seem arbitrary, but it is following those steps in the algorithm that I pointed out, right? And so right at the beginning, it's gonna randomly assign these guys different groups, and then it's going to calculate the centroid for each of those groups, and then it will reassign points based on the location of those centroids, and iterate until it arrives at a stable, non-changing centroid and non-changing assignment. And so that's really all there is to it. It's not, so, you know, for cluster 9, these would be all of the sort of stablest centroid points when I'm deciding how to make the assignments.
So if I try to do it again and later attempt the same data set, I should be able to come to the same.
Yep. Yeah. So generally speaking, even though the assignment at the beginning is random, I think it's the case that you will always converge to the same groups. I'm pretty sure, but don't quote me on that one. Yeah. Okay. Okay, and so I can take this function and kind of do the same thing for all of my other examples. Okay, so let's see here. I'll show you guys what this looks like one at a time. And let me first do this again. Okay, so here's example 2. So think in your mind about how you might expect the clustering to happen as we change the number of clusters. Here's example 3, and think about, start thinking about what you might expect the clustering assignment to look like. And example 4. Okay? So here we go. So actually here's a different example before I show the actual clusters. So this is for example 2. I've done between 2 and 25 clusters, and I plotted the within sum of squares, and you can see this is like a more typical kind of shape of an arm. And so, I don't know, where do you guys think the elbow is? Like 10, 11, something like that? Maybe 15? I don't know. So, some people talk about this rule about how the change in one, in your within sum of squares becomes less than the change horizontally. So, okay, anyways, we'll take a look. All right, here's example 2. And why don't I'm gonna pop this out so it'll be a little bit bigger. Okay, so you can see 2 clusters. It kind of bisects the data, and then 3 clusters, 4 clusters, and you can kind of see that spatially the groupings are maintained kind of in coordination, right? You don't have like random points in showing up in other groups. They're all, remember, based around distances to a centroid. We were saying somewhere between 10 and 15, right, is the correct number, is the quote-unquote correct number, but again, no validation here, of clusters. So yeah, you can see that might go all the way up to here. Yeah, visually speaking, what do you guys think? What would your choice of number of clusters be? Anyone want to hazard a? 14? Okay. Yeah.
I would say 8.
8? Yeah. So it really kind of depends, right? If you, there's no right answer here. And if I were to just plot this guy again, oops, not there, over here. Right, there's some question of like, is this a distinct cluster from this? What about these guys? Are these guys different? Is this supposed to be all one cluster, or are these different? Right, and so if you look at the plot again, not that one. Yeah, regarding, in some instances, those groups that I was pointing out would be together, and then in a different cluster they might be different. And there isn't really an ideal one, like even this one where maybe we've decided to separate these two, but then you have some problems over here, right, where this whole thing is separated into different ones. So especially ones that are clustered lengthwise in a direction, those might get separated, even though it looks like they're like clustered together. So those are some possible drawbacks. But we can make that a little bit more explicit, depending on the pattern. Let's look at number 3. Right, and so maybe this is not going to be quite what you expected, right? But this is all distance-based, and so, maybe you would ideally think that there's 2 clusters, but in that case, right, the centroid is probably going to be located somewhere in the middle of this group, and that means that the points in the top shoehorn have to be assigned to that because they're going to be closer to that centroid. And so similar to here. And so there is no configuration of number of clusters that's really going to let you escape that particular issue. Yeah?
Is there like a way to cluster more, like depending on like how close your neighbors are?
Well, we'll find out shortly, won't we? Yes. The answer is yes. There's going to be a couple of other clustering algorithms we're going to look at today that will be better at handling some things and probably worse at others, right? So. Okay. And the last one. Yeah, if anyone actually has this right in their heads, I would be very impressed. So here we go. Yeah, so this is what this last one looks like. And so, just in case you don't remember, here is the original right here. Okay. So really doesn't look anything at all like what we might imagine. And so we'll look at different algorithms that might better be able to handle this type of thing. And what I'll point out is that really this has to do a lot with sort of the density of data. And that can be an attribute that, that you decide to cluster on in a different procedure. But that k-means would not be able to handle well. Okay? All right. Let's do our next one. My iPad decided to restart for some reason. That's all right. Okay. So the next one we're going to look at is called hierarchical clustering. You may also have heard of this as agglomerative or bottom-up clustering. So this is an alternative method. Does not require pre-selecting the number of groups, or K. It's actually going to tell you all of the groups simultaneously. So this results in tree-based representation. Known as a dendrogram. Oop, there's no E. Okay. Let me see if I can draw this correctly. This goes here. All right. So let's have something like A, B, C, D. So these things are branches, and these guys are leaves. So the farther up the tree, branches begin to fuse, and the more different the leaf observations are. So no conclusions can be made on horizontal distances. So I actually don't know if A is closer or farther to C or D than B, because that's purely on a horizontal basis. It's all about kind of vertical branches and where they're fusing. So the way this works is you end up drawing a tree for all of your data, and this dendrogram here is actually already telling us all of the possible clusters. And the way that we do this is once you've drawn the tree and you say, okay, tell me what the assignments would be if there's 2 clusters, what you would do is you would cut right here. And this would be 2 clusters, right? You can imagine that I snip these 2 and I now have 2 separate objects. If I wanted 3 clusters, then I would do something like this here. And so cut here would be 3 clusters. And then if I wanted 4, you could cut right here. And 5 would be right here. And so on and so forth, right? And so you would separate out the leaves based on these cuts, and that would tell you the clusters. You can see that, if I cut to 3 clusters, right, you'd have this group here of 3, you'd have this group here of 3, and then you have A within its own cluster. Okay. Any questions?
How exactly do you draw this?
Yes. I will tell you right now. So similar to k-means, there's a simple algorithm for this. So algorithm, each observation is its own cluster. So we have n total clusters. Then the 2 most similar are fused. So you have n minus 1 clusters. And then we continue until a single cluster is left. Okay? So what does similar mean? I'll talk about what that is in a second. There's actually different ways we can think about similarity. But the general gist of it is I have a whole bunch of points. They each start out as their own cluster. You find the 2 points that are the most similar, you take them and you fuse the branches together. And then I continue and do that for all of the points until I've built up the entire tree. Okay? So, similarity can be on the basis of Euclidean distance. This is for individual points. So you figure out which ones are closest to each other by Euclidean distance. And then if you're trying to group points to if you're trying to group a point to an existing cluster, right, which may have multiple points, this is similarity on basis of linkage. And there's different ways of doing this. And so this is really thinking about your centroid. You have complete, you have single, and you have average. So complete is based on the largest dissimilarity within the group. Single is the smallest dissimilarity. And average is the average dissimilarity. Okay, so what that means is if I have, let's say I have 3 points, 1, 2, 3, or let me do 3. In the algorithm, let's say these guys get clustered together first. The way that I compare this guy against now this cluster of points is I can compare it against the thing that's closest, which would be single. I could compare it against the thing that's farthest away in that group. That would be complete. And then I can compare that against the mean, which would be the centroid. And so this would be average. Okay? Any questions or confusions here? All right. And actually, the choice of doing single, complete, or average makes a really, really, really big difference in the way that things are clustered. Average and complete tend to have more balanced clusters. And so by balance, we mean the number of points within a cluster are relatively similar. And single tends to have the least balanced clusters. Okay, so average / complete have most balanced clusters. Okay, let's take a quick break, and when we come back, we'll implement hierarchical clustering, and we'll see how that fares against the examples that we've shown already. All right, so we'll do 5 minutes.
I interpreted this like you were saying, it's like you need 19 when we were talking, like that's just like a lot. Yeah. So it's probably just means just do this for salary.
I don't really because you need to have like some line testing.
Well, yeah. So how I heard it was like
Here's where I decided to pick which
variable set, so just go through one by one, remove the first variable, remove the second variable, and then here's the right test criteria. So depending on which criteria I selected, I will calculate a criteria.
Also, you give it in the beginning, you say, oh,
Yeah.
I mean, yeah, you can do it. I just did that. That's all.
That was for so it's like but then
Number why this is negative.
Number four,
Like AIC smaller is better. But make it negative plus 5 is better because that's negative. That's what I
so you have like basically, I mean, that's why I'm looking at right now, it's just like, are we just doing wedding or like students or are we?
Yeah, so I actually rewrote the.
No, this is,
I didn't change any of the project.
That's what I'm asking, because
I made it
this
so that
kind of implies
it
that.
stored. You can calculate. Based on the criteria, so like figures out which one is the best.
Find the optimal
Criteria have
I'm just gonna ask.
this.
I think it's just salary, I think you're right.
Yes.
So for homework, free, problem 2.
Okay.
There's for the backwards stepwise selection,
Yes.
when you say like, produce the K models from the K variables in the hitters data set, are we just looking at the response variable of salary?
Yeah.
Or are you asking us to treat all the variables as response variables and iterate through?
No.
To okay. Because, okay, just salary.
Yeah. Yeah.
I way overcomplicated it.
Well, okay, that would be intense.
To be fair, the actual code is not that bad.
Okay.
But I do have
Yeah, just salary.
different like optimal AIC BICs.
Yeah, no.
Okay.
Just salary.
Cool. Makes it easy.
Yeah.
That's a thing.
That's just so I can like outline every step and understand it. Okay. So I did it for adjusted R, and then it worked. And then I chose that same seat for AIC and BIC. Because I started off by using the stepwise, and then you said no, you have to do it manually. So then I did maybe a little bit. Okay, so I did my adjusted R one, and I copied it, and I used it for AIC, and then I calculated.
That's fine.
I used the same
Honestly,
All right, guys, we're going to continue. Okay, so now we're going to show the implementation of hierarchical clustering in R. The way that we do this is with the function called hclust, which is stands for hierarchical clustering. Two main inputs here is the distance matrix, which you can, the distance matrix of your data, which calculates all the Euclidean distances between every pairwise set of points. And you can just use this function dist to do that, and that'll do it automatically for you, right? Because what hierarchical cluster really wants is thinking about how far the points are away from each other, right? And the second input is the method, complete, average, and single, as I mentioned before. Okay? So I can go ahead and run these guys, and then you can actually plot the entire tree, which I have the code for here. And so we're going to look at the trees one at a time to see kind of what they look like. Okay, and so lines 74 to 76, we've actually done the hierarchical clustering. Actually, you know what? We should kind of do the same thing and see what that actually tells us. If I put in hc.complete. So not much here. All it tells you is the clustering method. We're using Euclidean distances, right? And remember that if the distances are really different between your variables, you'll want to normalize or scale them in some way, and then the number of data points. All right, so let's look at the tree. Right here. So it's a lot of data points, right? So it gets pretty messy down here, but you can see how this kind of clustering looks. And so again, based off of the distances between the points, what did I say? Complete is based on the largest dissimilarity. Okay, so this is the complete one. And if you look at kind of, if I am making cuts to this tree to determine which cluster a particular point belongs into, you can see that if I cut up here for 2 clusters, the number of points here and the number of points here are going to be relatively close. Okay, and so that's what I was talking about with a balanced set of clusters. And if I do average, it'll be probably kind of similar. Yeah, so it'll look like this, maybe a little bit less balanced. But the big difference is in clustering with single. So you can see if I make a cut here, the 2 clusters would be something like these points against all of these points, right? And so this clustering approach tends to give you the least balanced set of clusters. Okay, and so what does that mean in application of actual data? We can take a look and see how they might compare. So let's see here. So I've written kind of my own function here that will do the hierarchical clustering across all of the metrics. And we can use that to look at the differences in the clustering approaches to the data that we have already examined. So let's take a look here. Okay, so now what's happening here is we're clustering in different ways. Okay, so as I go from here to here, it's 2 clusters, 3 clusters, 4 clusters, 5 clusters, and so on. The first row of clusters is using the average. The second one is doing complete, and the third one is doing single. Okay? So when we have 2 clusters, you'll notice that the average and complete look pretty much the same, but actually single, it cares about the thing that is least similar, right? And so it's going to group these 3 together and this one on its own. When we get to 3 clusters, they end up all looking the same. with 4 clusters, this is kind of our ideal one, right? From a visual perspective, they all look the same. And then here with 5 clusters, you'll notice the discrepancy. With average, it's going to, you can see at the corner of this group here, there's a couple of points in its own cluster, whereas in complete, it split this group in half, whereas with single, it's taken a single point out as its own cluster. Okay, and so you can see that type of thing happening, right? So things that are least similar, these points are grouped in their own clusters, as opposed to here, where incomplete, it splits, and then up there, there might be a couple of different points that end up getting clustered together. Yeah, so you can see that even the choice of the choice of linkage, right, which is the single, complete, or average, can make a big difference in the way that clusters are selected. You know, if we were talking about the ability of this particular algorithm to kind of get what we want, right, which is here, in this case, the hierarchical clustering is still doing, I guess, the sort of proper job from our, you know, visual inspection. But let's see how it does based on other types of groupings. Gotta do this guy first. Okay. Here is our example 2. So this one is using complete. And the types of things that you're seeing are probably going to be actually kind of similar to k-means. But in fact, I think it does a little bit of a better job, particularly on groups where you are spanning these sort of larger distances. We saw that when that was happening in the k-means, they tended to start splitting these guys. Whereas with hierarchical clustering, right, because it's all about pairwise distances between points, these guys end up kind of staying the same. And it'll split groups once you have too many clusters in, you know, slightly different ways, right? So you can see like these two groups get split when you're at the 25 clusters. And I think average is going to look similar to that. You probably won't notice too many differences, but if I do single, you can see that there's kind of a slightly different approach happening here. It basically groups everyone together, and then it takes the group that's like the most dissimilar and spits that out, as opposed to trying to like evenly apportion out where the groups are. And so here we can really note in cluster 2 with 2 clusters, everything's the same except for that top left. 3, it's the it's the left top and left middle. And then 4 and 5 and so on. You can see it's kind of pulling out groups one at a time, as opposed to kind of evenly apportioning them, right? And so that's a big difference with the single linkage approach. All right, let's look at example 3. So, where did I put my? So what do you guys notice here? Now, maybe if some of you guys were going to ask this question about when does it make sense to use the single one, right? In this particular case, you can see that by thinking about things as dissimilar, it's actually able to accurately characterize these two horseshoes as separate objects, right? Of which none of the other algorithms or linkages have been able to do successfully so far. Okay? Yeah, so this is really just to give you guys a flavor of the differences in how the algorithms kind of approach doing these clusterings and that they can lead to different results. Okay, last one. I don't know why I did that. Okay, what do you guys think? What's going to happen here? There's a lot of data points in this one, and so it might take a little while to plot. Cool. Also not great. So when we think about clusters that are spatially similar to each other, but that may overlap in places where they're kind of plotted, right, with horseshoes. K-means doesn't do such a great job, but hierarchical clustering is a potential solution. When we're thinking about these density-based problems, still not great. Okay? Yes?
What's the application of the clustering? Is it like descriptive or is there a predictive aspect?
Yeah, so it can be descriptive and kind of exploratory in nature, but sometimes you can actually use these things to create groups based on things in the data that might be difficult for you to observe kind of visually. And so, you know, you may be able to find like clusters that are based on certain attributes that might be difficult to identify otherwise, and then those factors you might then classify as things that define that cluster, right? And so you're saying maybe I observe a certain set of common attributes in this cluster versus this cluster, and then you're almost turning it into like a classification type thing where except that you didn't have the like requisite data on what those groups were to begin with.
Like
So
latent variables?
yes, yeah, latent variables could be an example of something that you could draw out using clusters. Yeah.
Okay.
Yeah, okay. So the last one we're going to talk about is the let's see. Density-based spatial clustering of applications with noise, also known as DB scan. So given a set of points in some space, it groups together points that are closely packed together. So this is like points with many nearby neighbors. And then marking as outliers points that lie alone in low density regions. So there's two parameters. Min points and epsilon. Okay, so let's talk about the algorithm. Slightly more complicated. Okay, so for each point in the data set, if number of points within epsilon neighborhood is greater than or equal to min points, classify as a core point. Otherwise, label as noise. And then step 2, we expand the cluster. For each point that is a core point, form a cluster. Any core points that can be reached is part of the cluster. Any noise points that can be reached but is less than or equal to the min points, add as border of the cluster. Okay, so this one slightly trickier to understand, but let's see if we can do this. So the two parameters that we talked about, right, is min points and epsilon. You can think of epsilon as the distance from any particular point. And so what I'm going to do is I'm going to draw this. This length is our epsilon. And then we're going to have minimum points equal to 4. Okay. I'm going to draw a couple of points in our data set. So imagine that we're on like a big x1, x2. Okay, so maybe something like this. And then a point out here. Okay, so the first thing we need to do, let me make sure I got this right. We need to classify things as core points or things as noise. And the way that I do that is I'm going to start with this guy right here. And actually, we'll just go left to right. That'll be easier. Okay, so right here, this guy. And what I'm going to do is I'm going to take this epsilon distance here and use it as a radius and draw a circle here. Okay? How many points are within the circle? 3. That's including itself. So 3 points. So if our minimum number of points is 4, then this is going to be classified as noise and not as a core point. Okay? So for now, I'm going to mark that as red. Now I'm going to do the same thing for this guy. And if I draw a circle around here, then you'll find, okay, this is a terrible circle, but you know what I mean. If you count the number of points, you'll find that it is at least equal to the minimum number of points and therefore gets classified as a core point. Okay, and if you were to repeat this procedure for every single point, you would find that it would look something like this. Okay? So that's step 1. So all of the core points, each point that's a core point will form the cluster. And then any core point that can reach that cluster is considered part of that cluster. And then any points, any noise points, right, that can be reached but is less than the number of minimum points. And so which ones would that be? Here. So does this reach the cluster? Yes, right? Because within epsilon, it contains core points. And then this one as well would reach the cluster, but doesn't have the requisite number of points, whereas this one does not reach the cluster. So what we do with these two guys is these become part of the cluster and they form the border of the cluster. And so once I've finished with the algorithm, I've got a cluster here and then a noise point here. And then you may have other clusters elsewhere. Okay? So this is the procedure that you would take to do, this is the algorithm that helps to generate clusters in a pretty different way, right, from all of the other ways that we've talked about so far.
Even though
Yeah.
they're orders, they're still a part of that cluster. They're not like designated something different. They're the green.
Yeah,
ones, right?
yeah,
They're still part of the
they are,
cluster.
they would be considered part of that cluster. Yeah, yeah.
How would you determine what epsilon to use and what point to use?
Yeah. Let's take a look at that. So what I'll do, so for our DB scan example, we need a couple libraries. We need the DB scan library. I'm also going to use the FNN library and the FPC library. Okay, so let me show you what it looks like with a default value of epsilon or like a self-determined, and then I'm going to talk about, then I'm going to show what happens as we change epsilon a lot, and then we can talk about strategies to determine what's the right epsilon. So DB scan, KNN dist plot, EX1, X comma Y, K equals 3. All right. So first, to determine the number of points, so we're going to first talk about procedures to think about the minimum number of points. We can do this distance plot, and it'll tell you points sampled, right, sorted by distance. And this kind of tells us what you would expect at different numbers of clusters. And so I could do this for different numbers of groups. K equals 4, and for 5. Here, and here, and they don't change very much. And so because the elbow plot doesn't change very much, what ends up happening is you can kind of go with the sort of smallest number. And so here we're going to do minimum points of 3. But it is connected directly, right, with the size of your epsilon, because depending on how you scale the epsilon, that would change the number of minimum points that you might want to look at. So we have to look at the other dimension as well. So let's see here, FPC, DB scan. And I'm going to plot this so we can see what this looks like. Okay, so if I did minimum number of points is equal to 3 with a 0.8 epsilon, we end up getting something like this, okay? Right, and so you don't get to choose the number of clusters. Those are entirely based on the data. And you can actually see here that in this group, because it's less dense, we actually end up with a couple of additional clusters. And then anything that's black, right, that's just left out as noise. So those are unassigned clusters. Okay? And let's take a look at what happens if I go across a range of different epsilons. Let me plot these guys. Okay. So it can be difficult to directly infer the correct epsilon, right? Because it's very context dependent on your data. So you don't really have a great rule of thumb necessarily on what the correct epsilon is. It'll be a little bit of a trial and error. And we can see what happens as I vary my epsilon from 0.5, right? Which means that the circles that I'm drawing are very tight, which is going to separate out a lot of clusters when you have data that's not very dense, okay? And as your radius on the circle gets bigger, it will better handle the data that's like less clustered together. So we can see that happening here. And at a certain point, you know, epsilon 1.5, you know, this group here, you're essentially saying group together points that are sort of less densely clustered and allowing that to become kind of one cluster as you increase the size of your epsilon. Okay? All right, and so I'm just going to kind of do this exact same procedure for the other examples, and we can see how differently dbScan kind of approaches doing this. Okay. Let me actually. Okay, so here is my groupings for the second example, broken out by increasing epsilons, right? And you can see as you increase the epsilon, it's going to categorize clusters together more and more. And you'll actually see that at a certain point, distinct clusters end up getting melded together because the search space for a single radius becomes large enough. So whereas at point 8, I've treated all of these guys as distinct clusters, once that search space is large enough, it's actually connecting these groups together. Okay? Right? So as soon as that epsilon is able to include a core point from, let's say another cluster, then all of that becomes one cluster. So you'll see eventually, if epsilon is large enough, all of your points will converge into a single cluster. Okay? Let's see how it handles the third example. Yeah, and so in this case, right, dbScan might actually be ideal for something like this because it's looking at kind of distance from each point individually. And so if they're separate in space, then they'll never really get to belong into the same cluster. And when the epsilon is really small, you have this issue where the groupings are not dense enough for it to consider to be one cluster. But pretty quickly, right, once we're at like 0.01, 0.011, the epsilon is large enough to put all these guys into a single cluster, or almost, right? You still sometimes have some stuff that gets clustered out. But yeah. Okay. And what do you guys think? Will this be able to handle the last one? Yes, that's like what this was built for, right? So we can see, hopefully, it'll be able to do its job. And a lot of data points in this one.
Like, how would you go about choosing what you want your epsilon to be?
Yeah, so it's a little bit of trial error, and also there are actually some metrics with which you can use to anchor epsilons to test from actually the elbow chart, I believe. Let me show that in just a second. Did I actually plot this? I did. Okay, here we go. Yeah, okay. So we have a couple of distinct shapes, if you guys remember. This is the one that none of the other clustering algorithms were really able to handle. And you can see as we increase the epsilon, it's sort of able to distinguish these clusters a little bit better. And so it's kind of up to you where you think certain grouping should happen. There were two kind of lines here. At a certain point, those end up getting grouped together in the same cluster. But the kind of important thing is a lot of the dead space in between, right? Those don't end up getting classified into the clusters because they don't meet the criteria for minimum number of points within a search space. So here, yeah, we can see that this is kind of the only algorithm that we've talked about today that really is able to handle sort of density-based clustering. Okay, and let me see here. Yeah, I'm trying to remember. There's I should, so let me get back to you on this, but I think it has to do with like anchoring the epsilon has to do with I think the ratio, something about the ratio between your k choice and I did not write this in my notes. Let me see. No, I think that's wrong. Okay, I need to get back to you on that. I don't actually, there is like a rule of thumb that people go by when they at least start trying ranges of epsilons, but I can't remember off the top of my head how we choose that anchor point. So I will get back to you next class on that. Yeah.
This density base seems to be pretty solid way of doing this, but then in one location will we use the other ones instead of this one?
Yeah, well, so I'm hoping that you'll see that certain types of data may better be addressed by a certain type of clustering algorithm. So a DB scan isn't necessarily the best for all sorts of approaches, right? In fact, I think that it probably performs the worst out of all of them at like the first example. So if I plot this again, in both k-means and hierarchical clustering, right, we were able to group, the visual set of clusters pretty easily, right? Both the k-means and the hierarchical clustering across all linkage types was able to successfully break them out into 4 clusters. Whereas dbscan here, if I were to ask if these points belong to this cluster, probably most people would say yes, but here they're not, right? They're considered noise. So in fact, I actually think that dbscan doesn't do so well when you have lots of groups that have that may have different densities associated with points within the cluster. Yeah, and so there, some other clustering algorithm might be more appropriate. But if you are specifically doing density, then this ends up doing really well, right? And so really the context of your data can kind of drive what the best clustering algorithm is that you should be using. And that may, when it comes to actually making a choice of what algorithm, you might actually want to try a couple of algorithms to start exploring with and seeing kind of how they perform and splitting up the groups in your data and if it makes sense, and then make a decision based on that. Yeah, and so a lot of this is, again, kind of exploratory in nature. You have a lot less to go off of because you never have any tools to do validation against like a classification, right? The colors here don't actually exist. The groups don't exist in the data. Yeah.
And this is based on the distance, right? So I can see as the radius. So what if my scales are very different? Like for example, my y scale is like 0 to 1, and my x scale is like 1 to 1,000.
Yeah, so that is really, really important when you're doing any distance-based clustering. You have to normalize or you have to scale your data. Yeah, if you don't do that, it will look like complete nonsense. It will derive all of the clusters based on only one axis, essentially. So, if you imagine that each of these was 1,000 times larger, then all of the clustering would be based on distances between points this way, but not this way. Yeah, so it's really important to do scaling and normalization in any distance-based clusters. Okay? Yeah, that's it for today. See you guys next week.